Hi, I'm Dr. Hidayah from Faculty of Science and Marine Environment, University Malaysia Terengganu. So today's topic is about ocean dynamics. We will focus on Egmont theory and upwelling. This video was made for teaching purpose in MARE project under Erasmus program of the European Union. And the objective of this topic is first to understand the concept of Egmont theory. The second one is to use the application of Egmont dynamics towards the upwelling system. Okay, so let's first look at Egmont theory. Egmont theory is first introduced to the scientific world by Wilfred Egmont, Swedish scientist, in 1902. So according to the theory, Coriolis force is in balance with frictional force. So what is Coriolis force? Coriolis force is the force that coming from the Earth rotation, and frictional force is from the wind stress. So according to Egmont theory, there is Egmont spiral and there is also Egmont transport that we need to know. So what is Egmont spiral? Egmont spiral is a spiraling movement of currents from the surface towards a deeper depth, about 100 meter. So at the surface current will deflect 45 degrees from the wind direction to the right in the northern hemisphere and to the left in the southern hemisphere. And for the Egmont spiral, it will decrease exponentially with depth as it turns clockwise in the northern hemisphere and counterclockwise in the southern hemisphere. Then Egmont transport is the resulting of the Egmont spiral. Add up together the magnitude, the direction of the spiraling, we will get the net water transport 90 degree to the right from the wind direction in the northern hemisphere, and we will get 90 degree to the left from the wind direction in the southern hemisphere. Egmont dynamics, it starts with winds blowing parallel to coastline over the ocean surface, and it will create surface currents. So not all surface currents will move according to wind direction. Some of it will deflect at 45 degree from the wind direction due to Coriolis force. And at the same time, we have frictional movement that cause surface current to create another motion downward as the water gets deeper. And that spiraling pattern, we call it Egmont spiral. And if the magnitudes and direction of that movement of each layer were added together, the result at the upper 100 meter is 90 degree relative to the wind. 90 degree to the right at the northern hemisphere and 90 degree to the left at southern hemisphere. So here is the schematic diagram showing how this Egmont dynamics cause net water movement 90 degree. And then, as we know, Egmont dynamics, it will cause one process in the ocean called upwelling, downwelling. So what is upwelling and what is downwelling? So upwelling is more people want to study it because it will give productivity in the ocean. So what is coastal upwelling? So coastal upwelling, it occurs where Egmont transport move surface water away from the coast. And then surface waters are replaced by bottom, nutrient-rich, cool water from the deep ocean towards surface. So what is coastal downwelling? Coastal downwelling occurs where Egmont transport moves surface water towards the coast. So the water will pile up at the coastal area and sink. So in this area, there is no high productivity occur. So when we are talking about the Egmont dynamics, the theory, and also the upwelling, so where does upwelling occur in this world? So there are 4 world major systems of upwelling that mostly associated with one system of currents we call eastern boundary current. So we have California current, we have Canary current, we have Benguela current, we have Humboldt current. So all these currents are responsible for the upwelling in these 4 major ocean systems. So what is eastern boundary currents? So eastern boundary current is the eastern portion of the oceanic gyres. So wind blow parallel to the coast towards the equator. So from the northern hemisphere, it will move towards the equator. From the southern hemisphere too, it will move towards the equator, and it will generate large scale of outwelling. So usually this upwelling system, it creates high ocean primary productivity. This is the figure of chlorophyll A concentration from satellite. So we can see at all upwelling area there is high primary productivity. So next, in 1990, Bacon has hypothesized that global warming will result in considerable changes of land-sea pressure gradients, and this will affect global wind patterns and resulting in increasing of outwelling intensity. Outwelling intensity tends to increase in the poleward but decrease in the equatorward. So this is by some researchers also found that outwelling intensity tends to increase in the poleward but decrease in the equatorward portions of the outwelling systems. So from Zhu et al. 2018, they make a schematic diagram showing how present outwelling and how future prediction of outwelling. So this conceptual diagram show that future changes in deep nutrients, longshore winds, wind stress curl, coastal upwelling, and also eddy activity. So in the future, differences in the isopycnal deepening between the gyre and the coastal regions, more nutrients are transported to the coastal area. So enhanced in future also, they predict that they will have enhanced local longshore winds that promote more coastal upwelling, and changes in the eddies, wind stress curl that will promote more upward nutrient flux in the offshore region, which study by Zhu et al. 2018. This study support Bacon hypothesis in 1990, where Bacon said global warming will make outwelling more intense. So that's all. Thank you.